Hyperbolic functions. In this section, I will define the hyperbolic functions and then talk a little bit about the algebra of them, and then we'll talk about the calculus of hyperbolic functions. Basically, the hyperbolic functions are combinations of e to the x and e to the negative x that occur frequently enough in mathematics and engineering. They've been given these special names. We define the hyperbolic sine of x, abbreviated sin h of x, as e to the x minus e to the negative x divided by 2. And the first graph on this page shows the graph of f of x equals hyperbolic sine of x in red, and notice how it's bounded by the graphs of e to the x over 2 and e to the negative x over 2, or negative 1/2 e to the negative x, I should say. And again, it's the graph in red. Similarly, the hyperbolic cosine is defined as e to the x plus e to the negative x over 2, and it's in the second graph, again in red. Again, notice how it's bounded by 1/2 e to the x and 1/2 e to the negative x. And if we divide the hyperbolic sine of x by the hyperbolic cosine of x, we get the hyperbolic tangent of x. And its graph is given in the third graph. Notice how it's bounded by y equals 1 and y equals negative 1. And now there are similar relations to what you've learned in traditional trigonometry. If you remember, in traditional trigonometry, if we took the sine of x and divided by the cosine of x, we got the tangent of x, and we see that similar relationship with the hyperbolic sine and cosine. The hyperbolic sine divided by the hyperbolic cosine yields the hyperbolic tangent. We have similar reciprocal relationships. 1 divided by the hyperbolic sine results in the hyperbolic cosecant. 1 divided by the hyperbolic cosine results in the hyperbolic secant. And the reciprocal of the tangent, the hyperbolic tangent, results in the hyperbolic cotangent. As with traditional trigonometric functions, the hyperbolic functions also have various identities, and a lot of them are similar to their counterparts in traditional trigonometry. The hyperbolic sine of negative x is equal to negative hyperbolic sine x. The hyperbolic sine is an odd function. Hyperbolic cosine of negative x is equal to hyperbolic cosine of x. The hyperbolic cosine is an even function. You might remember some Pythagorean identities for traditional trigonometric functions. There are similar identities for the hyperbolic functions, but they're a little different. So you might remember that sine square plus cosine square of any angle is 1. Well, it's a little different. Hyperbolic cosine x square minus hyperbolic sine x square is 1. So notice, big difference, that it's a subtraction in this identity between the hyperbolic cosine and the hyperbolic sine. And as a result, then, there's a different Pythagorean identity relating the secant and the tangent, again with a difference of the sign, S-I-G-N, sign. The sum identity for the hyperbolic sine is a little bit different. Again, it's with the S-I-G-N sign, and similarly for the hyperbolic cosine. But otherwise, they should look pretty much the same. Actually, for the hyperbolic cosine, it's actually the correct sign. So just be aware of those. We're not going to use those identities too often, but just be aware of them. As with traditional trigonometry, with the hyperbolic functions, we may occasionally need to verify or use identities. So here we're asked to verify the identity that the hyperbolic cosine of x subtract the hyperbolic sine of x is equal to e to the negative x. As with traditional trigonometry identities, it's often easier to start with the more complicated side. So I'll start with the left and use some definitions and work from there. So let's start from the left. Hyperbolic cosine x minus hyperbolic sine x, using their straight definitions. Hyperbolic cosine is e to the x plus e to the negative x divided by 2. And then we're subtracting the hyperbolic sine. Well, that's e to the x subtract e to the negative x over 2. Now these are two fractions. They have the same denominator, so I can immediately combine them to a single fraction. And so that would be e to the x plus e to the negative x. I don't really need those parentheses, but I'll leave them there. Now I'm subtracting the entire second numerator. This second set of parentheses is pretty important. And the common denominator is 2. Distributing that subtraction. So I now have e to the x plus e to the negative x, subtract e to the x, add e to the negative x, and that's still divided by 2. And now we might notice that in the numerator there are a couple of like terms that go to 0. E to the x minus e to the x, those go to 0. And the other two terms combine. And so I now have 2 e to the negative x divided by 2. And simplifying the fraction does leave e to the negative x. And so we have verified this identity. And so then this is true for all x. Here's another identity. Maybe you'd like to try this one out on your own. As I did with the previous example, I'll start with the more complicated side, and to me the right-hand side looks more complicated, so I'll start with it. Alright, so I have hyperbolic cosine square x plus hyperbolic sine square x. So let's see. I'll start by rewriting these with their definitions. The hyperbolic cosine is e to the x plus e to the negative x, and that's being squared over 2, and then that's being squared. And then similarly, I'd have e to the x minus e to the negative x over 2, and that's being squared. So now I'll square these terms, being very careful here. If I square the numerator, e to the x plus e to the negative x, that's a binomial squared, so I'd have e to the x squared, that's e to the 2x, and then I'd have plus 2 times e to the x times e to the negative x, and then I would have e to the negative x squared, and so that would be an e to the negative 2x. And then I'd have over 2 squared, which is 4. Similarly, in the second fraction, I'd have e to the 2x minus 2 e to the x e to the negative x. And then finally, I'd have a plus e to the negative 2x, again over 4. Now I can write this as one big fraction. And we might say, well, can we simplify any of this? In particular, what's this e to the x times e to the negative x? Well, if you remember your rules for exponents, e to the x times e to the negative x, that would be e to the x plus negative x, and so that would be e to the 0, which is 1. So I can simplify this a little bit along the way. While writing this as one big fraction, I would have e to the 2x plus 2 times 1, that's a 2, plus e to the negative 2x. And then I'm adding that entire second numerator, so that would be a plus e to the 2x, a minus 2, and a plus e to the negative 2x. And if we look at the like terms now in the numerator, I've got a plus 2 and a minus 2, and so those go to 0. Those combine to 0. And the other terms combine. So let's see, I'd have a 2e to the 2x, a plus 2e to the negative 2x, and that's all over 4. Well, I have a common factor here of 2 in the numerator and denominator. So let me divide out that 2, and so I'd now have e to the 2x plus e to the negative 2x over 2. And if you look at this, this is the definition of the hyperbolic cosine, but instead of an x, we have a 2x. And so this is, in fact, the hyperbolic cosine of 2x, which verifies the identity. Now let's start looking at some calculus. We wish to differentiate y equals the hyperbolic sine of x. Well, we don't have a formula yet, so let's start from what we know. I know that y, using the definition of the hyperbolic sine, well, that's e to the x minus e to the negative x over 2. And now let's calculate the derivative. So then y prime, well, that's the same thing as a 1/2, so let me bring out that 1/2. And then I'd have the derivative of e to the x minus the derivative, d by dx, of e to the negative x. Fortunately, we know how to do those. So I'd still have that 1/2. The derivative with respect to x of e to the x is e to the x minus the derivative with respect to x of e to the negative x would be e to the negative x times chain rule, a negative 1. And so then y prime would be 1/2 of e to the x plus e to the negative x. And if we look at that carefully, maybe rewrite it a little bit, that's e to the x plus e to the negative x over 2. Well, that looks like the hyperbolic cosine of x. So if the original function is the hyperbolic sine, its derivative is the hyperbolic cosine. That should sound familiar. If our original function was the sine, its derivative was the cosine. It works as well for the hyperbolic functions. Alright, so what if we had the hyperbolic tangent of x? How could we find its derivative? Now would be a good time to pause. Maybe try this one out on your own. Alright, so the trick with this is, again, use the definition. We know that if y is the hyperbolic tangent, that's the same as the hyperbolic sine divided by the hyperbolic cosine. So let's start from there in calculating the derivative. So then y prime would be, I'll use the quotient rule. So let's see, I would have the low function times the derivative of the upper function minus the upper function times the derivative of the lower function over the lower function squared. Now we have a problem here. I have not shown what the derivative of the hyperbolic cosine is. So let's do that real quick. The derivative of the hyperbolic cosine was d by dx of the hyperbolic cosine of x. Alright, so that would be d by dx of e to the x plus e to the negative x over 2. And so then that would be 1/2 of, let's see, we'd have the derivative of e to the x is e to the x. The derivative of e to the negative x would be e to the negative x times a negative 1. And so that would be 1/2. I'd have an e to the x minus e to the negative x. And so that's e to the x minus e to the negative x over 2, which is the definition of the hyperbolic sine. So be careful, the derivative of the hyperbolic cosine is exactly the hyperbolic sine. There is no negative involved, like there was for the traditional trigonometry. Alright, so y prime would be hyperbolic cosine x. The derivative of the hyperbolic sine is the hyperbolic cosine minus the hyperbolic sine of x, and the derivative of the hyperbolic cosine is, again, the hyperbolic sine. We just showed that. And that's over the hyperbolic cosine square of x. So then y prime is hyperbolic cosine square x minus hyperbolic sine square x over hyperbolic cosine square x. And now we use one of our identities back from a previous slide. Hyperbolic cosine square minus hyperbolic sine square is the equivalent to the Pythagorean identity for traditional trigonometry. And so that then yields 1 over hyperbolic sine square x. And so then y prime is hyperbolic secant square x. And again, we see a similarity to what we learned in traditional trigonometric functions. Remember that if our original function was the tangent, its derivative was the secant square, and we see a corresponding relationship with the hyperbolic functions. For your convenience, I now list the derivatives of the 6 basic hyperbolic functions. We've shown the first 3 for the sine, the cosine, and the tangent, or the hyperbolic sine, cosine, and tangent, I should say. We could similarly prove the derivatives for the hyperbolic cosecant, secant, and cotangent using similar ideas. These should probably be committed to memory. Let's look at a couple of examples now with more complicated functions. Here we're asked to differentiate y equals hyperbolic cosine of natural log x. Using the chain rule, then y prime would be the derivative of the hyperbolic cosine is the hyperbolic sine of the quantity. Using the chain rule then, times the derivative of the natural log of x. So y prime would be hyperbolic sine of natural log x times 1 over x. Or we can write that as hyperbolic sine of natural log x over x. Our second example, we have that y is the hyperbolic sine of the hyperbolic cosine of x. And so now we will again apply the chain rule. Y prime would be the hyperbolic cosine of the hyperbolic cosine of x times, by the chain rule, d by dx of the hyperbolic cosine of x. And so then y prime would be hyperbolic cosine of x times hyperbolic sine of x. Now let's evaluate a couple of integrals. Let's see, we're asked to evaluate first the integral of hyperbolic sine of 1 plus 4x dx. This looks like a classic substitution. If I let u equal 1 plus 4x, then du would be 4 dx. So let's see, I would need to bring in a factor of 4 to give me the du. And so I would need a 1/4 outside the integral to counter that. And so then I would have the integral of 1/4 of the integral of hyperbolic sine u du. Since the derivative of the hyperbolic cosine is the hyperbolic sine, then the antiderivative of the hyperbolic cosine would be, the antiderivative of the hyperbolic sine would be the hyperbolic cosine plus a constant. Going back to the original variable, I would have 1/4 hyperbolic cosine of 1 plus 4x plus a constant. If we wanted to integrate the hyperbolic tangent of x, we use the same trick that we did for learning how to integrate the traditional tangent function. And that we will rewrite this as the integral of the hyperbolic sine of x over the hyperbolic cosine of x. So just using the definition of the hyperbolic tangent, now we'll make a substitution. We know that there's a relationship between the hyperbolic sine and the hyperbolic cosine, and that they're derivatives of each other. So if I make the substitution, if I let u equal the hyperbolic cosine of x, then the du is the hyperbolic sine of x dx. And we see that that shows up already. So we don't need to actually bring anything else in with this substitution. And so then this becomes the integral with the substitution 1 over u du. Well, that's an easy integral. That's natural log absolute u plus a constant. And so then, substituting back, I would have natural log absolute hyperbolic cosine of x plus a constant. And then we might remember, well, wait a second, the hyperbolic cosine, if we think about the graph, it's always greater than 0, the hyperbolic cosine is. And so I actually don't need those absolute value bars. And so I can write this more simply as just natural log of hyperbolic cosine x plus a constant. So now let's see an application and learn how to use these functions on our calculator. We're told that the Gateway Arch in St. Louis was designed by Eero Saarinen and was constructed using the equation y equals 211.49 minus 20.96 hyperbolic cosine of 0.03291765x. For the central curve of the arch, where x and y are measured in meters and absolute x is less than or equal to 91.20. We're asked to graph the central curve. Alright, so let's find where this function is on our calculator. If we bring up our calculator, and I'll bring up the y equals screen, so I've got to turn it on first. Let's go to the y equals screen, second, and F1, there's my y equals screen. And now, let's see, I'd have 211.49 minus minus 20.96. Now I need to bring up the hyperbolic cosine function. So if you go into your math menu, alright, so I'll hit second math, and scroll down a while until you get the C. So there's C. See it has hyperbolic? Go to the right, and there are your 6. the 6 traditional hyperbolic functions and their inverses as well. We're not going to worry about their inverses, but you might have to deal with those in a later course. So I need the hyperbolic cosine function. I'll hit enter. And now I need to type in, let's see, 0.03291765. Close that off. Hit, oh, don't forget the x. Alright, now hit enter. It's in there. We're asked to graph this where x and y are measured in meters and absolute x is less than or equal to 91.20. So let me go to my window. And so then, since I want to see the x values between 91.20 and positive 91.20, I'm going to go a little bit further. I'll go from negative 95 to 95. I'll use a scale of 5s on the x. On the y's, I'm really not sure where to start. So I'll go from, well, I'll go from negative 5 meters, just so I can, it'll be easier to see the axis, the x-axis now, as opposed to if I started at 0. And for the y maximum, let's start with 100 meters. And I'll use a scale of 5s again. Alright, so now let's look at the graph and see what happens. Alright, so I see some of the graph. I don't see all of it, so let me adjust my window. I need to move the y max up. So how about I move the y max to, how about 250? Let's try that. So I see this graph. This looks like a reasonable graph. It appears to show, the ground level, and I see a highest point. And this graph looks like a parabola, but it's not. This is not equivalent to a quadratic function. It has a special name. It's called a catenary, and graphs of hyperbolic cosine functions are those catenaries, C-A-T-E-N-A-R-Y. So there I've graphed the curve. Alright, and there's a graph, there's this, the screenshot of that graph of the central curve. And we're asked, what is the height of the arch at its center? So, what is this center value? And we can actually do this without the calculator. What's the height of the arch at its center? Well, that would be what is the value of y when x is 0. And so that would be 211.49 minus 20.96 hyperbolic cosine of, and if you multiply all that times 0, we would get 211.49 minus 20.96 hyperbolic cosine of 0. And the hyperbolic cosine of 0, well, let's see, what would that be? Let's do that out on the side here, a little side work. The hyperbolic cosine of 0 would be e to the 0 plus e to the negative 0 over 2. And so that would be 1 plus e to the 0 again is 1 over 2. And so that would be 2 over 2, which is 1. And so then the hyperbolic cosine of 0 is 1. And so that ends up being 211.49 minus 20.96, which is 190.53, and that would be in terms of meters. We can verify this on the calculator since we already have the graph up. There's our graph, and all I would do with this graph is I can trace. So I'll hit F3 and type in 0 and hit enter. And so I see then 190.53, and so that agrees with what I had. Using the same curve, we're now asked at what points is the height 100 meters? Alright, so to figure this out, we would have to solve an equation. We'd have to solve where is y equal to 100. We don't know how to solve this equation using analytical techniques yet. We would have to use an inverse hyperbolic function, and I'm not going to deal with that in this course. So instead, we'll solve it graphically. So I'll solve graphically. So let me again bring up the calculator. There's our graph, and now I'll put in a second equation at y equals 100 and regraph it. And now I can calculate these points under the math menu, intersect, and the first curve, it's always a good idea to get close to the point of intersection. So my first curve is the hyperbolic cosine curve. My second curve is the line. My lower bound, go to the left of where you think the intersection is, hit enter, and the upper bound, move right of where you think the intersection is and hit enter a second time. And I see that that occurs when x is negative 71.56. If you run the intersection again, you'll find that x is also equal to positive 71.56. And we can sort of see the symmetry in the curve. You might have been able to guess that after the first one. And so then at what points? The points would then be at positive or negative 71.56, comma 100. And so both of those are in meters. What is the slope of the arch at the points? Well, to figure out the slope, we would need the derivative. And so then using our rules for derivatives, we can write that y prime would be then negative 20.96. The derivative of the hyperbolic cosine is the hyperbolic sine. And we'd have the 0.03291765 x. And then by the chain rule, we would have to then multiply that by the derivative of the inside, which is just, again, a 0.03291765. Alright, so now we would calculate this. So this isn't going to be a whole lot of fun to calculate, but we can. So we'll use the home screen for this. And let's see, I would need to type in now, when x is 70, let's go with the negative 71.56 first. So I need, what is y prime of negative 71.56? And again, then what is y prime of positive 71.56? Alright, so that would be then negative 20.96 hyperbolic sine. So again, I need to go to the math menu, scroll down to C, bring up the hyperbolic sine, and then I'd have 0.032911765 times negative 71.56. Close that off, and then I'd have to multiply that by the 0.032911765. And I'll hit enter. Let's hit green enter to be sure that we get an approximation. And that's 3.60483 to 6 decimal places, or 5 decimal places. And then I'll just change out that negative to a positive to get the other value. So let's delete, or let's backspace on that negative and hit green, enter again, and we get the negative. Not surprising considering the hyperbolic sine is an odd function. So y prime of negative 71.56 is 3.60483, and y prime of 71.56 is negative 3.60483, and each of those slopes, so notice that on the left-hand side we get a positive slope, not surprising. The right-hand side we get a negative slope. Again, not surprising looking at the shape of the curve. Alright, that completes this presentation.